Uh, Mwalimu Arnold Sekago as usual. So today we are going to discuss about some of the important theorems in abstract algebra, and those are the isomorphism theorems. We are going to discuss those theorems, their statement, and how to prove them. So we have the first isomorphism theorem. First isomorphism theorem. A moment. First isomorphism theorem. So here is the statement. Here is the statement of the theorem. Statement. Let phi be a group homomorphism. A group homomorphism. Let phi be a group homomorphism from group G to H. So G and H are groups. Be a group homomorphism. Let me also include it. G and H. G and H. These are groups. They are groups. Then the group factor canal of phi, group factor. This factor group is isomorphic. This is isomorphic to phi of G. In general, what we are saying here is that this factor group is isomorphic to the image of that map. This factor group here is isomorphic to the image of that map. So we are going to prove this statement. So how would you prove that this is isomorphic to that? So we are going to define our map. Proof. We are going to define a map F from G to phi of G by F, by F. So we are having a map from a factor group to phi of G. So you have to think about how the elements within this group look like. How do we represent elements within this factor group? So you remember, this factor group is structured in such a way that this is a subgroup of this, and this consists of elements which are cosets. So elements within G factor n, elements within this group, they look like this. An, such that A is an element of G. They are cosets. So here we shall have A, K being equal to phi of K, where A is an element of the group and this K is equal to canal of phi. We are going to define this map by that. Now, you have to be very careful with this definition. You have to first check and see whether this map is well defined. Yes. So we have to check and see whether our map is well defined. So to check whether this map is well defined, if AK is equal to BK, if I pick two elements from this factor group, and those two elements are equal, if they are equal, then this should imply that phi of A is the same as phi. Sorry. This is, that's it. If two elements are the same here, then both of the two images, the image of A must be the same as the image of B. So if we are able to prove that, then the map is well defined. So if A K is equal to BK, if two elements within the factor group are equal, what do you think? What do you think is the implication of that? Think about it. This means that, this implies that A inverse B is an element within the kernel. You can do some cancellation. You can bring this A this side. For example, you have AK equals BK. You can do something which is similar to this. So we shall have K being equal to A inverse BK. So this implies that A inverse B is an element within the kernel. Yes, that is the implication of that. And similarly, we can also have if you do cancellation on this B, it's the same as saying that B inverse A is within the kernel. It's also fine. It's fine. Now we are having this element within the kernel. So if it's within the kernel, then it is mapped to the identity. Hope you know that. It's mapped to the identity. If this element is in the kernel, then in fact it is within the kernel. To be more elaborate, it is within the kernel phi. That means phi A inverse B is equal to identity. And we know that phi is a group homomorphism. So we can come up with something of this sort. Phi B equals E. That's what we are having. Then after that, by properties of group homomorphism, I can write this as phi A inverse phi B equals E. Some cancellation, I want to bring this side, so I'm going to multiply with phi of A on both sides. Phi A inverse phi B, this is equal to E phi A. So this and this is the identity. This is the identity. So I will have phi of B being equal to phi of A. Hence the map is well defined. So my map is well defined. That is the first thing. You have to first show that that map is well defined. Pick two elements from this group, then show that their images are the same. If you were able to prove that, then the map is well defined. Now we are going to prove that F is an isomorphism. We are going to claim that F is an isomorphism. So what do we have to prove here? We have to show that if F is an isomorphism, this F, we have to show that this F is a group homomorphism. We have to show that F is a group homomorphism. Then we also have to prove that it is a bijection. In particular, we have to show that it is a bijective homomorphism. A homomorphism which is surjective, and at the same time a homomorphism which is injective. Yes, that's what we mean by saying that F is an isomorphism. So we have to show that F is a group homomorphism. We also have to show that F is one-to-one or injective homomorphism. We also have to show that F is onto surjective homomorphism. If you are able to prove those three cases, then F is an isomorphism. So we defined F as F is mapping the factor canal of phi to phi of D. We define this by F AK equals phi of A. We are going to show that F is a group homomorphism. We are going to prove that F is a group homomorphism. So we are going to let AK and BK be elements from that factor group. Then F of AK BK, this is equal to, so we have picked two elements from the factor group. Hope you remember the binary operation which is defined on a factor group. So if I compose these two elements, I'll come up with F A B K, and by definition, if I'm having this, then this from this fact, this should be mapped to phi of AB, and phi is a group homomorphism. So this is equal to phi of A, phi of B. But phi of A is F of AK, and this is F of BK. So in particular, we have showed that this is equal to F of AK, F of BK. So this implies that F is a homomorphism. F is a group homomorphism. Yes. Now next we are going to show that F is one-to-one. F is one-to-one. Remember, if you are supposed to prove that a given map is one-to-one, if you are supposed to prove that, then we have to pick an element from the kernel, and we show that that element is mapped to the identity. In particular, this is what I'm meaning. F is 1 to 1. F is 1 to 1 if and only if the canal of F consists of the identity element. That is the interpretation of a map being 1 to 1 or injective. So we are going to pick an element from the canal of F, and we show that that element is mapped to the identity. It's what we are going to prove. Yeah, then if you are able to prove that, then the map is 1 to 1. The map is 1 to 1. So by definition, canal of F consists of those elements. AK consists of those elements AK from G factor canal phi such that those elements are mapped to the identity F AK is equal to the identity. By definition, that is the definition of the kernel of that map. Those elements which are mapped to the identity. Elements such that if you apply this map, they will be mapped to the identity. So I'm going to remember I'm supposed to prove this. I'm going to let AK be an element from the kernel of F. Now I have to show that that element is the identity. If I'm able to show that, then kernel of F is equal to the identity. So if AK is within the kernel, if AK is an element from the kernel of F, so this implies that this is mapped to the identity. It implies that that thing is mapped to the identity, and in particular, F AK, which is phi A is equal to the identity. So if I'm having phi A being equal to the identity, if I'm having that situation, so the interpretation of that is that element A is mapped to an identity element. Yes, this A from the group is mapped to the identity element, and this should imply that this A is mapped to the identity. So A is within the kernel of phi. So A is within the kernel of phi. So if it is within the kernel of phi and it is mapped to the identity, then we shall have, this implies that we shall have AK being equal to an identity element. So in this proof, let me repeat once again. I've picked an element AK from the kernel of F. So if AK is within the kernel, that means AK will be mapped to the identity, and this means that phi of A will also be an identity element. So in particular A is mapped to the identity, so A is within the kernel phi, and if A is within the kernel phi, that AK will also be equal to the identity. So in particular, we have kernel of F being equal to K, being equal to the identity. So it's consisting of an identity element. So this implies that F is injective. F is injective. Next, we are going to prove on 2. We are going to prove 2. We are going to prove that the map is on 2. And indeed, that map is onto because reason being, for each phi of A in phi of B, for each element from the image, for each element from the image, there exists an element AK within the domain, such that F AK is equal to phi A. Hence, the map is surjective. For each element within our image, for each element in the range, pick an element from the range, you will be able to find the coset corresponding to that element. Hence, the map is surjective. So combining 1, 2, and 3, combining the fact that F is a group homomorphism, F is 1 to 1, F is onto, therefore F is an isomorphism. So we are going to come up with some examples about this important result. So the examples, we are going to first recap this theorem, the statement of this theorem. So the statement says, examples, recall from the first isomorphism theorem that F G factor kernel of phi is isomorphic to phi of G. We have that. Or you can say that it's isomorphic to the image of G. So let us take some examples. We have this important example. Number 1. This group here is isomorphic to Zn. Let me hope that you're familiar with this group, that factor group. N is an integer. This N being an integer which is greater or equal to 2. Which is greater or equal to 2. For example, before I explain this, let us first recap how the structure of such groups how such groups are structured. For example, if n is equal to 2, if n is equal to 2, I'll have something of this sort. If n is 2, I'll have this factor group here. Now, elements within that group, they are cosets. They are cosets, and here we have elements here coset. You have 0 plus 2z, comma 1 plus 2z. These are the elements within that group. So we want to make a claim that this group is isomorphic to Z2. We want to make that claim that that group is isomorphic to Z2. So we are going to prove that using the first isomorphism theorem. So the first isomorphism theorem states that G factor canal of phi is isomorphic to phi of G. So that means that if I want to prove that this is isomorphic to that, it's enough to show that. Okay, let me first define this map. Let me first define the map. Define the map from f sending z to zn by f of a equals elements which are equivalence classes. Yes, equivalence classes. Yeah, within Zn, within Zn. So if I'm able to show that the canal of this mapping, if I prove that the canal, if I show that canal, we show that the canal of f is equal to nz. If I'm able to prove this, if I show that the canal of this map is nz, then by the first isomorphism theorem I'm done. Because the first isomorphism theorem states that G factor kernel of phi is isomorphic to this. So just prove that the kernel of this map here is nz. So that the kernel is nz. Then by the first isomorphism theorem, we shall be done. So let us first show that this map of ours is a homomorphism. The homomorphism. So I'm going to let A and B be elements in Z. Then I'll have f of A plus B being equal to A plus B, and this is equal to A plus B. This is f of A, this is f of B. Note that here I'm using addition because the binary operation defined on both of those groups, two groups, is addition. So I'm having this. I'm having f of A plus B. This is equal to f of A plus C, f of B. and this should imply that F is a homomorphism. F is a homomorphism. Now I'm going to work out the canal of that map. Yes, and see whether the canal is NZ. So we are going to compute the canal of F, canal of our map. So the canal of F by definition, canal of F is equal to elements within Z, elements in Z, such that under F, those elements are mapped to the identity, the identity within Zn. So the identity here is 0. By definition, that is our kernel. So we are going to work out the kernel. We have f of a being equal to 0. And this f of a, by definition, this f of a is equal to this equivalence class of element a. And by definition, this implies that a is related to 0 mod n. Is equivalent to 0 mod n. So you are an element here. You are an element here if at all. For example, let me give you a simple example of 4 is congruent. 4 is congruent to 0 mod 4, and also 16 is congruent to 0 mod 4. The reason is simple. This 4 divides 16. 4 divides 16, and the remainder is 0. So what is here is already the remainder. So here, this 4 divides 4 and the remainder is 0. 4 divides 16 and the remainder is 0. So you are within the equivalence class of A. If at all you have a remainder 0 when n divides you, you are within the equivalence class of A. If at all the remainder is 0 when n divides you. Yes, by definition, that is the interpretation of that. So here, such elements which will give us a 0, elements which will give us a 0 when divided by n. What do you think those elements are? Elements which will give us a 0 when divided by n. Those elements are multiples of n. Yeah, multiples of n. So such elements which satisfy this are of this nature. Of that nature. So in particular, we have our kernel of F as NZ. And indeed we have proved that, but we can also check and see whether F is onto. Yes, F is onto. Let's check and see whether F is onto. So, and indeed this is very easy to check. This is very easy to check that F is onto if this is within Zn, then phi of A be equal to this. Hence, phi is equal. So by the first isomorphism theorem, let us conclude by the first isomorphism theorem, comma, z factor nz is isomorphic to that. We are going to take another example. We are going to take another example of an important group. Example 2. In fact, I should leave this as an assignment. Try to check whether you have understood. Try to check and see. So question 2, we have this general linear group over R factor, the special linear group. This is isomorphic to H, is isomorphic to H, where this H is, let me say that, where this H is the multiplicative, H is multiplicative group of non-zero real numbers. So this is a group in which elements within that group are matrices. Matrices, 2 by 2 matrices, but the elements within the rows and columns are real numbers, yes. And this is the special linear group, yes, special linear group. Now we are claiming that this group factor that is isomorphic to the multiplicative group of non-zero real numbers. So we are going to prove that, yes, by applying the first isomorphism theorem. We are going to define our map. We are going to define a map F from that by f of A being equal to determinant of A. That's what we are having. We are defining our map by that. So for us to show that this is isomorphic to that, we shall just prove that the kernel of this map is the special linear group. Yes, special linear group. And in particular here we are saying that this group this group H is a multiplicative group of non-zero real number. We don't have we are setting a situation in such a way that we are restricting ourselves to those matrices which are invertible. Yes, to the matrices which are invertible, because if this H is a multiplicative group of real numbers which are zero, then this group will be consisting of some of the elements which are not invertible, yes, and yet it must be by its structure, it is consisting of elements or members whose inverses are not zero, whose determinants are not zero. So groups which are matrices which are invertible. Matrices which are invertible. So we are going to show that SL2 is the kernel of that map. So let us speak. A moment. Let A and B be elements from our group. So I want to show that F is a homomorphism. Yes, F is a homomorphism. Yes, F is a homomorphism. So we shall have F. Note that here I'm multiplying. Yes, the operation on that group is multiplication. So this is equal to determinant of AB. And from properties of determinants, this is the same as determinant of A determinant of B. Determinant of A is f of A, determinant of B is f of B. So F is indeed a homomorphism, since f of AB is equal to f of A, f of B. So this should imply that F is a homomorphism. F is indeed a group homomorphism. Now I'm going to compute the kernel of F. I'm going to work out the kernel of F. Now we are going to get the kernel of our map. So the kernel consists of elements A, such that these elements are mapped to the identity. Now you need to think about the identity in H. Yes, and that identity is one. The identity within the multiplicative group of non-zero real numbers is 1. So in particular, we have f of A, which is equal to determinant of A. This is equal to 1. So we have matrices which are mapped to 1. Matrices whose determinant is equal to 1. What do you think those matrices are? Matrices where their determinant is 1. Those matrices form the special linear group. They form the special linear group. So kernel of F is equal to SL2 over R. Such matrices form the special linear group. Now we are going to check and see whether F is onto, let us see. So if A, pick an element from the image, if A is within the image, then we shall have F A 0, 0, 1 being equal equal to, this will be determinant of this matrix, and determinant of this matrix is equal to. So I've been able to pick an element from the range, and I've been able to show that this element has a, should I call it an object? Yes. Which object is this matrix? So for each element which you pick from the range, you will be able to get an element which is mapped onto it from the domain. So indeed, by the first isomorphism theorem, we have this group here, factor SL2 being isomorphic to multiplicative group of non-zero. So I'm going to stop here. In the next session, we shall discuss about the second isomorphism theorem. Don't forget to subscribe to my YouTube channel.